Out in the dark void of space sits a massive, boiling red supergiant, one of the most heavily scrutinized objects in the night sky. It is easily visible as the bright orange star marking the top left shoulder of the Orion constellation. This image shows the sheer physical scale of Betelgeuse. At 764 solar radii, if you placed it at the center of our solar system, its outer atmosphere would consume the orbits of Mercury, Venus, Earth, Mars, and the entire asteroid belt. Solitary supergiants of this size usually follow a steady rhythm. Internal pressure and gravity cause the star to pulsate, physically shrinking and expanding roughly every 400 days. This graph shows two conflicting rhythms. The 400-day pulse is expected, but layered over it is a second cycle known as the long secondary period, a 2100-day cycle of distinct dimming and brightening. Standard stellar physics cannot account for two overlapping, contradictory cycles of this magnitude. The internal models used to predict the star's behavior were missing a variable. The limit of these models was reached in late 2019, when Betelgeuse suddenly lost 60% of its visual brightness. This great dimming event caused an immediate reaction across the scientific community and the public. Many suspected the sudden drop in light was the final precursor to an imminent supernova explosion. Adding to the confusion was the star's extreme rotation speed. Betelgeuse spins at 5 kilometers per second. A star with an atmosphere this immense and diffuse cannot naturally maintain that momentum on its own. A 6-year dimming cycle, an extreme rotation speed, and a massive drop in brightness. The math for a solitary, dying star did not add up. Astronomers realized they had to look for an external force acting upon the giant. In early 2026, researchers presented a solution. They aggregated nearly 8 years of archival space telescope data to find what internal models missed. Peering through the blinding glare of a supergiant to spot a hidden object is virtually impossible. Instead of looking for light, researchers tracked the subtle, long-term movements of gas surrounding the star. This spectral heat map isolates those gas movements. The data revealed a repeating, dense trail of plasma. It was behaving exactly like the wake forming behind a boat as it cuts through water. A wake requires an object to plow through the material. This repeating structure was the direct proof astronomers needed. A physical companion was carving a path through the star's extended outer layers. The companion star is formally known as Siwarha. It is a pre-main sequence star, meaning it hasn't fully initiated nuclear fusion, and its mass is roughly equivalent to our Sun, making it practically a speck next to Betelgeuse. Tracing this orbital model, Siwarha completes one full orbit in exactly 2100 days, matching the 6-year dimming cycle. This continuous gravitational pull acts as an engine, transferring momentum and spinning Betelgeuse up to its extreme rotation rate. This orbital path also dictates the events of 2019. That year, Siwarha reached periastron, the absolute closest orbital point to the giant. That close pass acted as a gravitational trigger. It ripped a massive bubble of hot plasma from the star's interior, creating a surface mass ejection, blasting outward at over 300,000 miles per hour. Moving away from the star, the ejected plasma cooled into a dense patch of silicate dust. That dust cloud settled directly into our line of sight, blocking out the light and explaining the 2019 false alarm. The fact of Betelgeuse belongs to a dynamic binary system changes how we calculate its remaining lifespan. This diagram illustrates the soon theory. If the star's 400-day pulse is the dominant structural mode, the core is in its late stages of fusing carbon, causing a collapse within decades to centuries. However, mainstream models use new binary mass measurements to argue it is safely in its helium-burning phase, placing the supernova 100,000 years away. Determining whether the core is currently fusing helium or carbon will reveal the star's exact expiration date. When the core finally runs out of fuel and collapses, the first warning sign will be completely invisible. Hours before any light reaches us, neutrino detectors here on Earth will register a massive spike. Then, the visual light will finally arrive. The supernova will reach a magnitude of -12, making it roughly as bright in our sky as a full moon. The explosion will be bright enough to see in broad daylight for several weeks, and it will cast stark shadows at night for nearly 2 years. As this distance scale shows, Earth sits well past the 160 light-year kill zone. At a safe distance of 724 light-years, our atmosphere will protect us from any ionizing radiation. The confirmation of Siwarha resolves a decades-old observational mystery. It isolates the exact physical mechanism currently interacting with the star and shaping the eventual explosion. We finally know exactly what is stirring the giant.